All right, let's start. So today we are going to talk about neural tangent kernels. First, I'm going to briefly overview, the kernel methods and the kernel trick in learning, and then I'm going to talk about specifically neural tangent kernels and what are the success and failure stories of them. All right, so let's again start with our favorite learning method, which is linear regression. Everything is simple in linear regression. So basically, we have a data set with endpoints, xi's and yi's. Let's, for simplicity, assume the labels are in real and the xi's are in d-dimensional space. And we are going to consider a linear model. So I'm going to show my model with this function f, w, and x. W represents my model parameter and x is my input. So for simplicity, I'm even ignoring the bias term. You can put, 1 in your x as one of the features and absorb that bias term in this model. So this is a simple linear model that we are considering. And the loss function that we often use is the quadratic loss. So we have the loss function in this form that I'm looking at the difference between my output and f of w x. This is my yi hat. So this is my prediction. I'm looking at the squared difference between them. And the objective is to minimize this loss and pick a model parameter w for that. All right, so this is a convex optimization, unconstrained convex optimization. That is good. We know how to solve it. We use gradient descent in order to solve this optimization problem. And I'll just write one update at iteration t that we use. I'm going to show my weights at iteration t plus 1 with wt plus 1. It is going to be equal to wt minus or learning rate that can actually be, depending on the iteration, gradient of my loss function, right? So gradient of my loss function evaluated at wt. Right? So what is this gradient? So this gradient is nothing but gradient of this quadratic function. So we have yi minus f wxi times the gradient of f wxi with respect to w evaluated at wt, right? So what is this term? What is the gradient of f wtxi with respect to w? And my f is this. Good, so it is just xi, right? It's a linear model. Gradient with respect to w is x, so this is nothing but just xi. So the interesting thing here is that here we, this term does not depend, it is static. Right? It doesn't depend on wt. So it is just xi. Xi is fixed because it's a training set that we have. It's a sample from the training set. And we know for sufficiently small learning rate, we have shown a few times, I think in the last lectures, that we converge to global optimizer for this optimization. All right, so what is a kernel method? Now I want to introduce a little bit of a nonlinearity to my model. So instead of considering my features, my samples xi's in d dimension, instead I'm going to look at the transformations of them, potentially in a larger dimensional space than the dimension that we had before. So this d, capital D, can be significantly larger than the small d. So it's a nonlinear, potentially this is a nonlinear transformations of my input. Right? Just to give you an example, suppose your D is 3 and your X's are in this form, X1, X2, X3 with 3 features. Now, instead I'm going to look at the transformation of X, let's say with polynomials of degree 2. So I'm going to look at X1, X2, X3. So these are my features. And I'm going to look at X1 times X2, X1 times X3, X2 times X3, so on and so forth, right? So I can expand my feature space using different nonlinear, potentially nonlinear functions that we have here. So a little bit of an abuse of notation here. I'm representing X1, the first feature of my X. Don't confuse it with, you know, the first sample X1 here. Okay, so all right, so we can use this in our model. And let's say our model is still in the form of f, w, and x, w transpose, but no, instead of x, I'm going to replace it with phi of x. So this is the model I'm going to use in my prediction. So question, is this model linear in W? Is this model linear in W? Good, so the answer is yes, right? So I haven't done anything. So X is my input, X is fixed, it is my training data, I can transform it with whatever. So the point here is that this phi transformation is fixed, right? So unlike neural networks that we optimize over these transformations, here it is fixed. I pick a particular transformation and I'm good. So I can argue that basically the model is linear in parameters X, but is it linear in X? Is the model linear in X? Yes, obviously no, right? Because of this nonlinear transformation, even though we are assuming this transformation is fixed, nevertheless, there's a nonlinear model that we have in it. So it is kind of, you know, the best of the two worlds, right? So we wanted to have a linear model in the model parameters, because that's where we are optimizing our model. That's the space that we are optimizing our model. And still, we are going to have a convex optimization in W. But here we have a little bit of a nonlinearity in our mapping X, and that's good. So here the optimization we have is the following. So we are minimizing, again, let's say a quadratic loss. Instead of x, I'm going to replace it with phi of x squared. And then use gradient descent. Again, this is still a convex optimization. So this is convex optimization. So gradient descent with a sufficiently small learning rate is going to converge to global optimizer of this optimization problem that we have here. Okay, so then it is good, but what is the issue here? So why don't we use this? If this is the best of the two worlds, why don't we use this in practice instead of deep models? So I have nonlinearity here, and it is convex, right? So that is pretty good. Okay, very good answers. Yes, the first point here is my phi is fixed. Right? How do I know what nonlinearity I should use to transform my data? So it is fixed. It is not very satisfying. And the second issue here is that we may suffer from curse of dimensionality, especially if my transformation, it lives in a much higher dimension than my input dimension. D can be significantly, as I mentioned, larger than small d. So to give you just a feeling about this, suppose your transformation is just a polynomial with degree, let's say, less or equal to k. So the example that I showed you, it is a polynomial with a degree 2 that you're looking at just the combination of the, the two features at most. So in this case, you can clearly see that D is going to be in the order of the small d to the power k, right? So before we had, in this case, it is like d to the power 2. If you have a degree k, you'll have a d to the power k as the dimension of your transformations. And let's say if we want to evaluate this on ImageNet, so on ImageNet, roughly speaking, images, they have 100,000 pixels. And let's say if k is 3, so your d would be order of 10 to the power 15, which is really, really large, right? So you can even potentially store these transform samples in your memory, because it is going to be very, very expensive. So here comes the kernel trick to save us. Kernel trick. In many learning algorithms and methods, we don't actually need to deal with phi of x's individually. So what we, in most of the cases we need is to look at the inner product between two transform samples, phi of xi and phi of xj. Right? So if that is the case, I'm not saying it is always the case, but in many instances, this is the case. We may be able to have a closed form solution for this inner product between the transform samples xi and xj, and we define it as the kernel value between samples xi and xj. So you can think about this, roughly speaking, as a measure of similarity between these two samples measured by this transformation phi. So this is called kernel function. And I can define also similarly a kernel matrix with a bold K. So this is a kernel matrix. It is in n by n. If I look at kernel similarity of all pairs of my training samples, I have n training samples, so it's going to be a matrix n by n, and the ith element of this is nothing but the kernel value between xi and xj. So this is a kernel matrix, and this is the kernel function that we have here. So this kernel matrix has nice properties. Obviously, it is symmetric, because if you just look at the definition of this kernel function, you'll see the symmetricity here. It is also positive semi-definite. It's a PSD matrix. And you can easily see that because this is basically the inner product of the two transformations of your input samples. All right, so the idea of the kernel trick is that in many cases, all right, so one way to compute this kernel is to compute these transformations phi's, right? And then compute the kernel value. But we don't like it because we don't even want to explicitly compute these transformations of inputs. But in many cases, we can come up with a closed form solution for this kernel function without explicitly computing these transformations of inputs. So as I mentioned, in many cases, without explicit computation of phi of x's, we can compute the kernel value between xi's and xj's. And if my optimization depends only on the kernel values, then I'm good, right? So I don't need to compute these phi x's, individually. So I can just compute the kernel between xi and xj. Right. So in fact, that is the case in many for many interesting transformations. For instance, you can consider polynomial kernels. Right. So we saw like one example of those kernels that you look at polynomial transformations up to a certain degree. And in that case, we can have a closed form solution for k as c plus, let's say, xi transpose xj to the power k. K is the power of the polynomial transformation that we are using to transform our features. All right, so here again, phi of x's, they live in a d-dimensional space. D is in order of d to the power k. It is really large. But what about this computation? So how much, what is the computational complexity of this computation? So we need to compute this inner product, which is order of d. And then that's it. That's, we just like add it up and look at the power of it. So the order of the computation that we have here is order of d instead of order of d to the power k. So this saves a lot of computational power and also storage power. All right, so that's basically called the kernel trick. So many interesting optimization problems that we have, you can kernelize. So you can, we have SVM, you can look at kernel SVM. So you kernelize them by rewriting their objective to only depend on the kernel instead of individual training samples. You have, for example, regression problem. Let's say ridge regression problem with the L2 regularization for the weights. So you can have the famous kernel ridge regression. You have PCA, you can look at kernelized version of PCA. So all of them, they basically use this trick. So they rewrite the objective to depend on the inner product, and then they replace the inner product with the kernel values. All right, so if we have time at the end, I may show one example of how to kernelize a method. But before that, I'm going to move on to talk about neural tangent kernels and see how it is connected to these kernel methods that I just explained. So I think it's a good time to pause. If you have any questions, please unmute yourself or post your questions in the chat box.
Can I ask a question?
Yes, please go ahead.
Yeah, two questions. First, how does I'm familiar with the kernel definition as like the zero mapping of transformation. Is there any relation to this definition, or I don't see the connection?
So here the kernel function is actually defined by this, right? So this is the kernel function that is the inner product between these transformed transformations of your inputs.
Yeah, no, I'm asking, is there any connection to the standard kernel definition of being like the null space of a transformation? I guess I'm just curious why they use the same exact terminology.
So there are a lot of other terminologies for kernels. So I'm not quite sure what you mean by that. Maybe we can talk about that specific definition offline and see if there are connections with this particular definition.
Second question was, how does the expressivity of this kernel, or like a polynomial kernel, change with the exponent? Because it seems just like taking power 2 or power 3 doesn't really change much if you can reduce it to this the kernel trick, using the kernel trick, right?
It does, right? If you just think about, again, from a transformation point of view, so if your dependencies are in order 2, then by looking at degree 2 polynomials, you're basically linearizing those dependencies. If you have some correlation, some dependencies of order k, if you use a polynomial kernel with degree 2, it is not going to be successful. Right? So it kind of depends on the types of dependencies that you have in your data. And in fact, that's one of the issues of kernel methods, because in many cases you don't actually ahead of time know what is the right function to use in your learning. And the kernel method basically requires that you choose that function before basically looking at your data. Obviously, you can try different kernels and see which one works. But to answer your question, yes, the complexity, the power, the expressive power of these transformations, when your degree of polynomial grows, it grows. But the amazing thing is that the computational complexity doesn't grow. It remains in order of D. And that's basically one really magical power of the kernel trick in this problem.
Okay, thank you.
Sure. Any other questions?
The order D, like, is k not a variable for calculating the polynomial kernel?
Yes, it is not a variable, so we are not optimizing it. So in practice, what people do, they can, try an error, right? Different, values for k, and see which one works the best. But in the optimization, it is fixed. So we cannot optimize, at least within this framework, over the transformation, and therefore over the kernel function.
I just have a question.
Yes, go ahead.
Yeah, how the D for polynomial kernels, isn't it the same that we have to multiply every xi with every xj?
So you pick a subset k of your features, and you look at basically a multiplicative meta feature among them, and that's where the degree k comes into the picture.
Okay.
Okay, so let me move on. I see a question about overparameterization. Hopefully it will be addressed later on in the lecture. So now let's talk about neural networks, right? So that's the main focus here. So let's start with a simple neural network in D dimension as it is input, and with only one hidden layer. Let's say I have one hidden layer and I have a single output. This is my Y. Right, so let's define some notations. The weights, input weights to neurons, I'm gonna refer with actually I's. So these are vectors in the dimension, and the weights in the second layer, I'm gonna refer it with B's. So therefore, I can write the output of my neural network, which is again a function of W and X. Here, W is the set of all A's, the weights in my first layer, and BI's, the weights in my second layer. So I can write it as sum over these neurons that I have, and let's say I have M neurons here. Sum over BI sigma AI transpose X. Again, let's forget about the bias term. You can add it, you can observe it in your X if you want. All right, so that's the output of my neural network, but importantly, I'm going to scale this up. So I'm going to divide this by square root of n. And you'll see why this scaling is in fact important in the discussions of kernels. All right, so that's my neural network. And I'm going to use quadratic loss for my training. So the quadratic loss that I have is same as before, fwxi minus yi squared. All right, so I can write basically updates of gradient descent. Again, this is a non-convex optimization problem. If I want to look at minimizing W, loss of loss function with respect to W. But we know gradient descent is pretty good, so I'm going to write the gradient descent update for this optimization problem. So I have WT plus 1 is equal to WT minus my learning rate that can depend on theta. The derivative of my loss function that we saw, it is equal to basically this term. I times the derivative of fwxi, this is evaluated at wt with respect to w. All right, so even in linear model, if I use, instead of x, if I use phi of x, right? So in the updates that we had for the linear regression, right? So let's look at this. If I use phi of x instead of x, so this term is very similar to the term that we have here. It's basically identical. But what about this term? So what is the difference between the second term that we have in neural network updates compared to a linear model? Is there like a fundamental difference between the two? Right, so before, this term was either xi or phi of xi. It was static. It wasn't changing during the training. So in linear, so this term was fixed. So it wasn't changing during training. But here, so this is going to change depending on WT from the previous iteration. Right, so that is the main difference between the gradient descent updates and trajectories between a linear model and neural network, right? Quite obvious, in fact. Okay, so how do we solve this? We initialize weight, let's say with a normal distribution. And then we basically look at the gradient descent update. So I have W0, and then I updated, I go to W1, and then I updated, I go to W2, so on and so forth. Right? So that's the gradient descent updates that we have here. So W, remember, is the set of all weights that we have in our model. Now let's say we can plot this W, right? So this W, like if, let's say we just focus on the first layer weights, it's a matrix. I can look at this W in my initialization. This is W0. I can again look at my W's on the trajectories of my gradient descent. I can look at W2, it will be a matrix. Okay, so an interesting empirical observation that we have here is the following. So this is empirical observation. When the width of the network is large, then M, basically it is the width of the network is large. These matrices that we have here, W's across along the trajectory of gradient descent, they are almost static. It's kind of surprising, right? Because here W is the parameters of my model, and I'm optimizing over these parameters. Obviously, they change. Obviously, they are not fixed, right? So we go from W0 to W1. If they're exactly the same, then basically we are not learning anything. So that's what I'm explaining by being static or constant. But they are roughly speaking constant, right? So you look at the patterns that you observe. Let's say these are high values or these are low values, and you almost observe similar patterns across the trajectories that you have, especially and in particular when M, the width of your network is really, really big. If your M is small, you will see these matrices change quite a bit. You can see the patterns are different. But when your M is really large, these weight matrices, they change, but they change slightly. So, you know, roughly speaking, they have almost a static pattern in them. Right? So this is called lazy training. Right? So you can see where the laziness comes here. All right, so I want to emphasize it is not always the case, right? I just want to emphasize this again. Not always the case. Especially if your M is relatively small, you will see changes. And sometimes even if your M is large, you may still see these changes. So it is not always the case, but in some regimes, we observe these weight matrices, they are pretty close to each other. So they are roughly constant. So it doesn't mean the model will take longer to train. It means the changes that we have in the weights in order to go from the initialization to the point that will converge is in fact very small. So in the parameter space. So we don't go too far, right? So if your initialization is here in the parameter space, if your initialization is here, so the trajectories of gradient descent is very close to your initialization, right? So it stays in a ball around your initialization point. So this is basically lazy training. In contrast, in adaptive or in non-lazy training, you can have your trajectories can be really, really far. So it may not remain in a particular ball. So we observe this behavior in some of the deep model trainings. All right, so there's a question, why is the laziness a function of M? Hopefully it will be clear later on. Okay, so let me move on. So as I mentioned, this is an empirical, purely empirical observation. So we just, run gradient descent, we look at these weights and say like, oh, geez, so look at, the changes. It is not significantly changing from one step to another step. So they are almost static. So there are some changes, but not a lot. All right, so based on this intuition, perhaps we can write the first order Taylor's approximation of the model. It's because the changes in W is not large, so Taylor's approximation may not be too bad. First order Taylor's approximation. Around what? Around my W0, right? So the initialization, or I call it W0, initialization of my weights. So I have a function W and X. So if I write the Taylor's expansion, I'm going to get W0. So X is a constant, right? So X is training data point. So we are basically expanding or function around W, the model parameters. Plus, what is the second term? Gradient of my function evaluated at W0 times W minus W0, and plus, second order, third order terms that we are going to ignore. So this is the Taylor's expansion of the model around the initialization weights. Okay, so let's look at this model, this approximation. Is this model, this approximation, linear? By linear, I mean linear or affine. Good answers. Yes, it is linear in what? Linear in W. So that's purposefully, I didn't write that up. So this is linear in W. The answer is yes. Is this model linear in your input, X? No, it is not linear in X. Good. So why isn't it linear in X? Because the dependence on X comes from this gradient computation. What is this term? So you look at the output of your model, you look at the gradient with respect to W, evaluated at W0 for that particular X. So this is a vector with the length of the parameters that you evaluate for X. It is potentially nonlinear because you have nonlinear activations in your function F. So you can even think about this term as just the transformation of X, right? So this is phi X transpose. It's a transformation of X, potentially nonlinear. So it is familiar, right? So it is basically very similar to the kernel method, right? So in the kernel method, we had this transformation of X. The model was linear or affine in W, but it wasn't linear in X. So basically, it is the same thing. The only difference here is that this phi of X is defined as a gradient of my F with respect to parameters evaluated at W0. So here I basically, by just comparing to the kernel method, here my phi of X is just gradient of my output with respect to the model parameters. And that's it. That's my transformation. So if I use this transformation to define a kernel, because this is my phi of X, so I can use this transformation to, let's say, look at the similarities between two of my samples, Xi and Xj, using these transformations. So this is going to be a kernel value between Xi and Xj. So this kernel is called neural tangent kernel. That's it. You see how simple it is? Why neural tangent kernel? Okay, tangent, because here we are looking at the first order Taylor's approximation, right? So this is my tangent model. I'm looking at a tangent, let's say a tangent model Wn(x). So this is an affine approximation of my function Fwn(x) when I'm looking at the tangent plane at W0 for this function. So this is my tangent model. So this is called the neural tangent kernel. So this is a tangent model to a neural network, and obviously it's a kernel. So this is called NTK. Okay, so let me pause and take some questions if there are any. So basically the point here is that you give me a neural network. I initialize weights with any random initializations that I want. So I'm going to define this feature map phi of x as the gradient of my output with respect to parameters evaluated at initialization, evaluated at W0. So that is my transformation. Is this transformation going to change along the trajectory of gradient descent? No, right? Because here I'm just evaluating it at W0. And that's the key difference, right? So again, my transformation comes from the neural network evaluated at W0. So still, it's a fixed transformation. So everything that I explained in the first 30 minutes of today's lecture holds. My optimization is convex, everything is good. All right, so there's a question, why is the approximation linear in W? No, it is linear in W, right? Because it is an affine function with respect to W, because I'm just looking at the first order Taylor's approximation. So this is constant. It doesn't depend on W. It depends on W0, which is fixed. So this guy is also for a given input, it is fixed, right? So I'm just evaluating at W0. It's a gradient of my model with respect to parameters. So the only term that depends on W is this guy, W minus W0. So therefore, it is affine. Okay, so very simple concept. Neural tangent kernel. All right, so let's go back to basically the previous setup that we had. When my input is in D dimension, I had M neurons and one output. It's M neurons. So to make the dependence on M explicit, now I'm going to index everything by N. So I'm going to say my output is Fwn(x), just to make sure that we have this M as explicit parameter here. Even my kernel, I'm going to explicitly show the dependence on M. So here it is basically 1 over the square root of M, sum 1 M bi times or activation AI transpose X. So that's the function that we have here. So let's compute the neural tangent kernel for this model. So it is quite simple. So what is neural tangent kernel? How I can compute NTK for a model? So the only thing I need is to look at the gradient of my output with respect to the parameters. And then that will be evaluated at the initialization. And that will be my transformation for a particular X, phi of X. And that's it. So the inner product between phi of X1, Xi, and phi of Xj will give me the kernel value. right? So that's basically the computation that we want. So let's then first look at, let me just look at the time. Okay, I think we have time. So let me look at the gradient computation of this function with respect to, let's say, AI. So what is the gradient with respect to AI? So we'll have just one term. So we have 1 over square root of m. So we have bi. So the gradient of this guy with respect to AI will be sigma prime AI transpose xi times the gradient of the inside, which is basically just x. So it will be sigma prime AI transpose x times x. And what is the gradient of this function with respect to, let's say, bi? It is even simpler. You have the scaling 1 over square root of m. So it is basically just this term, right? Gradient with respect to bi. So basically I compute all of these gradients. I put them in one giant vector and evaluate it for x and x prime. And then I look at the inner product between these two vectors. And that will be the kernel value between x and x prime. Alternatively, I can just look at the kernel value that comes from AIs, and I can look at the kernel value that comes from BIs and just sum them up, because when I'm concatenating them in a vector and looking at the inner product, I'm basically doing the same thing. So the kernel value between x and x prime, again, I'm making this dependence on m explicit here. So this is my NTK computed with a neural network with m neurons. The width is m. So this is basically the kernel value that comes from the AIs. I'll just index it with A. And the kernel values that comes from the Bs. So it's just, you know, not to concatenate everything and looking at the inner product. So I just will look at the inner product of these features coming from the gradient with respect to A's, and I'll look at the inner product of features coming from the gradient with respect to B's and sum them up, right? Just to clean up some of the computation a little bit. So when I write it up, you'll see it is actually quite simple. All right, so what is it? Let's first write the kernel value that comes from A's. So this is my feature map, right? So this guy is my feature map. I evaluated for x and x prime, and I look at the inner product between the two. So I will get basically 1 over square root of m times 1 over square root of m. So I'll get 1 over m, right? So I'll get bi squared. And then I'll get sigma prime AI transpose x times sigma prime AI transpose x prime. And then I'll get the inner product between x and x prime. So that's basically the inner product between the two. So I'll have 1 over m. For the ith parameter AI, so I'll get basically bi squared, sigma prime AI transpose x, sigma prime AI transpose x prime. So these are numbers. At the end of the day, I'll look at the inner product between x and x prime. So x inner product x prime. And again, I'll sum it up over all of my i's, right? So these are inner products. So I look at the inner product chunk by chunk. So I'll sum it up over all of my m neurons that I have here. So what about the kernel value that comes from B's? The same story, right? So I have this value for bi evaluated for x and x prime, and I multiply them. So I get 1 over m, because 1 over square root of m times 1 over square root of m, I get 1 over m, sigma AI transpose x times sigma AI transpose x prime. And then I just sum it up over m parameters that I have. And that's it. That's the, for give me an x prime, these AIs and BIs, let's say we initialize with some random numbers. They're fixed. Again, I can just compute these values, sum it up, and that will be my NTK evaluated for between x and x prime. So this notation is just the inner product between x and x prime. Okay, so now you see some interesting behavior here. So let me actually pause. Is there any questions about this computation? So I think at home you should basically do this practice. I did it a little bit quick, but it is really simple. It's just the inner product between the two vectors of gradient with respect to the parameters evaluated for x and x prime. Okay, now let's see some interesting behavior, right? So here, this is the kernel NTK for a network with a width of m. And we look at the summation of these terms, and then I look at the basically a normalized version by m. So this is basically an average. So if I generate my AIs and BIs independently, then this is basically going to converge to the expectation. This is an empirical average over m, realizations of these AIs and BIs. So if I make m larger and larger, so this is going to converge to the expected value of them depending on the distribution that we are using to generate AIs and BIs. And that was the main reason that I use 1 over square root of m here, right? So the reason was because when I'm looking at the inner product, I want to get 1 over m here, and 1 over m summation over I from 1 to m, this is the empirical average exactly based on law of large numbers, will converge to the expectation. Right? So that's the argument here. So let's say AIs and BIs are independent samples from a distribution at initialization. So based on law of large numbers or any favorite concentration equations that you can use, inequalities that you can use, when m goes to the infinity, these quantities will converge to their expected values. So we'll get the kernel NTK that we used to have an index of m, it is going to converge to just the limit point, which is the expectation, right? So I'm going to just replace this summation, this empirical average with the expectation. So I'll get b squared sigma prime a transpose x, sigma prime a transpose x prime, the inner product between the two. So when I'm looking at the expectation, I don't need to look at individual realizations anymore. So b squared sigma prime a transpose x, sigma prime a transpose x prime, inner product between x and x prime. Similarly, for the kernel NTK evaluated using BIs, we are going to converge to a limit kernel sigma a dot x and sigma a dot x prime. So you can think about these kernels, these guys are NTKs, neural tangent kernels, coming from a neural network with an infinite width. Right? So these NTKs are from neural networks with infinite width. So if you see people, they talk about infinite width neural network, they are not like constructing an infinite width neural network. So they are looking at the limit of NTK when m goes to infinity, you get these expressions for your NTK. And in fact, you can compute these expressions in closed form. You don't need to even construct such a neural network in order to empirically evaluate it. these kernels. So that's the whole idea of the kernel trick, right? To explicitly be able to compute these kernel values between x and x prime. For instance, suppose, let's say my activation is ReLU, and let's say the distribution of AIs, these are vectors, are rotation invariant, is rotation invariant, like Gaussian with identity covariance. It's a pretty general distribution that you use to generate your initialization weights. In that case, I can further simplify these limiting NTKs. I can compute that the kernel between x and x prime is just the inner product between them, looking at the expectation of b squared over 2 over pi times pi minus the angle between x and x prime. So theta here is the angle between x and x prime, between 0 and pi. And similarly, I can simplify the formula for the NTK with an infinite width neural network for Bs, like this. So these are pretty algebraic calculations, but the point here is that cosine of theta plus sine of theta. But the point here is that now I have an explicit formula for my kernels coming from neural networks with infinite width. And now I can just use these kernels, as explained in the first 30 minutes of today's lecture, in my kernel machine. I can just use a kernelized regression and see how it works. So these kernels are presumably a little bit more powerful because they are coming from an infinite width neural network, so they may perform better than just polynomial kernels or other types of kernels for us. Okay, so let me pause and take some questions. Why the last assumption? We need this rotation invariant assumption. Otherwise, you won't be able to simplify to these equations for the kernel. So you don't want to depend on the angle that your particular x is. You want to depend on the angle between x and x prime. So you want to be rotation invariant. Okay, good. So let me move on. I want to cover two aspects of NTKs before we finish today. So then basically NTK is nothing but just like a kernel formula, comes from first order Taylor's approximation, and then looking at the limit of the transformation when we have infinitely many neurons, right, in our first layer. So you can define NTK for convolutions, for other networks as well. So there are a lot of papers on that subject. All right, so there are two questions that we want to answer, right? So the first question is when this approximation, when the Taylor's approximation is good, right? Because we want to understand or approximate the performance of a neural network with these kernels, right? Yeah, it's great that we can compute them in a closed form, but at the end of the day, the heart of the matter is this equation, right? So this equation that we have. So when this equation, when this first order Taylor's approximation is a good approximation, because here I argued that my weights, they don't change too much. So then it's gonna be a good approximation to use the first order Taylor's. So in many cases, you can show if the Hessian of your model has some bounded eigenvalues, has bounded eigenvalue. So this is basically the Hessian control that we discussed in the first 3 lectures. Then I can control the change in my gradients, right? And my transformation here, the phi transformation, only depends on the gradients of my model, right? So this is my phi transformation. So this depends on the gradients of my model with respect to parameters. So if the Hessian is somehow bounded, then I can argue that the changes in my transformations are not going to be large along the trajectory of gradient descent. So in fact, if you go back to the overparameterization lecture that we had, I think in the 2nd or 3rd lecture, so we showed for a one hidden layer neural network, in fact, that's the case. So the Hessian, when m goes to infinity, the Hessian goes to 0, and the gradient remains, roughly speaking, constant. So that's the power of the overparameterization. So for this part, I'm going to ask you to see lectures 2 and 3 on overparameterization. So for overparameterized model, this can be a good regime to think about, this approximation. All right, so next, what is, how we can analyze gradient descent under this NTK model. So I wanna, in the last 8-10 minutes, I wanna explain that part as well to finish NTK's argument, how we can analyze gradient descent. All right, so here, one particular form of gradient descent is called gradient flow when the learning rate goes to 0. So in that case, we call the dynamics the gradient flow dynamics. So in gradient descent, we have WT plus 1 is equal to WT minus my learning rate times the gradient of my parameters evaluated at WT. Now from here, I can just look at the finite length difference that I observed in my parameters. This is going to be equal to the negative gradient of my loss function evaluated at WT. And when I look at the limit, when eta goes to 0, when my learning rate is really, really small, so this will basically converge to some ODE based on the dynamics of my weights. So I can just write that as the change, the temporal change in my weights would be equal to the negative gradient of my loss function. So this equation is called gradient flow dynamics. Sometimes it is easier to start analyzing the models in this asymptotic regime when the learning rate goes to 0. Here we don't have a dependence, but it's still, it has, roughly speaking, the same fundamental properties of the gradient descent or even a stochastic gradient descent. Okay. So let's look at the quadratic loss. Let's say my loss is quadratic. Say I have y hats as my prediction at a particular w minus y. So these y's and y hats, they are in n-dimensional spaces. For each point we have a prediction. I'm just looking at the difference between the two. Right, so what is the gradient of this function with respect to w? We have done it multiple times. It's y hat minus y times the gradient of y hat with respect to w. So it's gradient of y hat with respect to w times. All right. So therefore, I can just plug this in this equation. So I'll get the gradient of w with respect to t would be equal to minus gradient of y hat. This is with respect to w, just want to be very clear, times y hat w minus y. I just plugging the gradient equations in this formula here. All right, so this basically shows the dynamics of my w in the parameter space, right? So how w changes in the parameter space. This is dynamics of weights in the parameter space. I can also look at the dynamics of my output, right? So how does my output changes along the path of my gradient descent? So in order to do that, I'm going to look at basically the derivative of y hat evaluated, let's say at wt with respect to time. So I want to see how my y hat changes along the trajectory of my gradient descent. So here I'm going to use a chain rule. Gradient with respect to t, I'm going to look at the gradient of w with respect to t, and then I'm going to look at the gradient of y hat with respect to w. And so that's basically the chain rule that we have. So gradient of y hat with respect to w times gradient of my weights with respect to t. So this is basically just chain rule. But now I have this formula for the gradient of my weights with respect to t. So that's basically this formula that we have here. So I can just plug that in this equation. So what I'm gonna get, there's a negative sign here as well, y hat. So what is this formula? This is the gradient of y hat with respect to w times y hat minus 1. So this is the dynamics of my y hat, how it changes along the trajectory of gradient descent. But something amazing happens here. So look at this term. So this is the gradient. So this is a vector of basically Jacobian computed basically for each sample. I compute the gradient with respect to weights, and I look at the inner product of gradient with respect to weights with, for pairs of samples. What is this? What is this guy? That's it. That's NTK. Right? So that is my neural tangent kernel. But here evaluated in generally at WT, but I know I can approximate it with my NTK, let's say my kernel evaluated at W0. So I'll basically get y hat WT minus y. I replace this with my NTK. So this is basically the dynamics of my output is my NTK evaluated at initialization times y hat minus y. So this is basically the approximation that we have here. So let's further simplify notations just to really be clear what we have here. So I'm going to define, let's say, u as y hat minus y. So this y is fixed, right? So this is my input data. My y hat is something that changes along the time. So I'm going to define u based on that. So the derivative of y hat with respect to t is equal to derivative of u with respect to t. So because y is fixed, so this is approximately equal to my NTK times y hat minus y, which is again u. Right, so that's basically the dynamics of my output. And this is probably the simplest ODE that you can come up with. So what is the solution for this ODE? It is just
Exponential.
Exponential, exactly. U of t is u of 0, e to the power minus this guy. And as you can see, when t goes to infinity, so this guy goes to 0, u goes to 0, it means y hat goes to y. So we get basically a zero training error. But something amazing also happens here. I know we are running out of time, but hold on like for 2-3 minutes just to finish this argument. Something really amazing happens here. So if you remember the overparameterization lectures, we argued that these tangent kernel matrices, they become positive definite, not positive semi-definite. So the minimum eigenvalue is bounded away from 0. So in overparameterization, parameterized case, so this guy, my tangent kernel, is positive definite. So the minimum eigenvalue, positive definite, is bounded away from 0. Right? So in general, we know kernels, they're positive semi-definite, but here we have a positive definite matrix. So let's see what happens in that case. So if I look at the eigen decomposition of this guy, so I have, let's say, lambda I, my eigen vectors vi transpose 1 to n. So I know all of my lambda i's, let's say lambda 1 greater than 0, less than lambda 2, less than lambda n. So all of my eigenvalues are bounded away from 0. Now let's plug that this decomposition in U. Let's see what we get. So we get the following, right? So we get u of t is going to be u0, and I'll have a multiplication because it's the exponential of e to the power minus lambda I vi transpose. Right. So you see, along the direction of my eigenvectors, lambda i's, my eigenvalues, they basically characterize the rate of convergence. So if all of my eigenvalues are bounded away from 0, then I'll have an exponential convergence to 0, and the minimum eigenvalue, in fact, will determine the rate of convergence, because that will be the slowest convergence that we'll get along the direction of the eigenvector. So that's the reason that we like overparameterization, because it guaranteed that we don't have 0 eigenvalue, and we'll have an exponential convergence in all of these directions. All right, so that's it about NTKs. Now we basically understand they're very simple to evaluate. So we have closed form functions for infinite width neural networks, NTKs for infinite width neural networks. And in overparameterized regimes, we see this approximation can be good, and we get exponential rate of convergence for the gradient descent. But I want to finish with this note that, in practice, there is still a significant gap between the performance of NTKs. Basically, you define your NTK and then run your kernel regression compared to deep learning. So basically, state-of-the-art neural networks often outperform kernel methods, even if they are based on NTKs. So NTKs improve the performance of kernel methods in general. So if you have a polynomial kernel, your performance is not going to be great, but if you use NTK, your performance is going to boost. But still, there is a gap between the performance of neural networks and NTKs, and because of that, and there are some also theoretical analysis that shows that NTKs, even though they're very useful concepts and important concepts, they don't fully explain what is going on in deep learning optimization and when we are looking at learning problems using neural networks. So lazy learning is good, but sometimes it is not the case in practice.